Our next speaker is Dr. Peter Eichhubl. He's a senior research scientist at the Bureau of Economic Geology, Jackson School of Geosciences at the University of Texas at Austin. His research areas include fracture mechanics, geochemistry, groundwater management, CO2 sequestration, as well as hydrogen storage and exploration and production of hydrocarbons. Peters, all yours.
Yes, let me share my screen here. And I need to share the sound. I didn't forget that part. All right, now switch to presentation mode. See what's happening. Try again. There we go. And I think I need to change my display. Is that correct?
No, it's fine now.
Is it correct now?
Oh no, you need to change it. Yes.
Oh, I need to change it back. All right. Okay. Correct now?
It's good.
Yes. Well, thank you, Dr. Seppenauer, for inviting me to present to this group. The previous talk by Dr. Delschat already provided the opening for my presentation, speaking about CO2 leakage and CO2 leakage pathways, and particularly emphasizing here the combined chemical and mechanical effects on leakage pathway formation. At the beginning, I would like to acknowledge my co-authors, postdoc Xiaofeng Chen, who did the majority of the work that I will be presenting, two grad students, John Major and Owen Callahan, and Professor John Olson, currently the chair of the Hildebrand department, who has provided his lab facilities and also contributed on the last part of my presentation, which includes some numerical simulations. This work was conducted with a DOE NATL grant and through the Center of Frontiers of Subsurface Energy Security, which was mentioned before, and then some funding from our research consortium. So CO2 is leaking to the surface in natural systems, and particularly in volcanic systems. It's common that volcanic CO2 leaks to the surface. And I'm showing here a slide, an image from Mammoth Mountain in California, which is volcanic, and it looks really like a doomsday scenario with the dead trees. So occasionally CO2 burps up from the magma chamber and comes up along faults and fractures as shown in that cartoon. Okay, pull up my pointer here. On the right side here, and then it seeps to the surface. What makes it more dramatic in this case is that this place receives a lot of snow in the winter. It's a ski area. They get 3-4 meters of snow routinely, and that snow cover traps the CO2 in the ground. So rather than the CO2 coming up at a spot and then getting into the atmosphere, it actually stays in the ground over the winter months, and that kills the trees and kills the vegetation on the ground. So it's exacerbating the effect here. As Dr. Duncan already emphasized, the personal risk is probably low. One concern could be that, as shown on the right side here, is that CO2 could accumulate in the basement of a house. We don't have basements in Texas here, so we're not worried about that. Other concerns are actually the economics. Number one, perhaps if you inject CO2 into the ground, you want it to stay there. If once it escapes, you lose your efficiency of the CCS process. So making sure the CO2 stays in the ground in the injection reservoir is obviously of economic concern. And then also should mention, as shown by Dr. Delschat, that the CO2 could migrate into overlying aquifers. Those could be drinking water aquifers and could create a contamination risk. So there's the CO2 and brine that would co-migrate with the CO2, and then potentially some once the CO2 interacts with the groundwater, you could have some leaching of minerals, and that could affect drinking water quality. So there's another reason that we want to minimize CO2 migration out of the storage reservoirs. And as the USGS slide on the right shows, the primary concern about leakage are existing faults and fractures. So that's what I'm focusing on here. Natural CO2 leakage is not necessarily limited to volcanic areas. There's one area in Utah where there is CO2 leaking naturally in a sedimentary system. And the source of the CO2 comes from different sources. I'm not going to talk about this. It manifests itself as little springs in the ground where the CO2 is bubbling up. There are travertine deposits, and then curiously there is a geyser. It's a cold water CO2 geyser. Unlike Yellowstone, where it's boiling water, this is not. It's cold, and it's actually that part is not natural. So the CO2 seepage is natural, but the geyser is not. It comes out of a well bore that was drilled in the 30s, and you don't see the pipe here, because this thing erupts maybe once in 24 hours, and I have been there many times, and it always erupts when you're not looking. So in this case, you walk away, and then sure enough, 5 minutes later, it erupts. So catching this guy in action is really hard. You have to be very patient, and I'm not patient enough. So that's kind of a curiosity, but it demonstrates that CO2 can leak in sedimentary systems as well. And in this case, also, it is located along a fault, a normal fault, which is shown in this Google oblique Google view as the dashed line. That's the trace of the fault. The stained area here is where the active seepage is of the CO2, but there are fossil seepage sites, travertine deposits all along the trace of this fault. And there's the Green River here. So this is in eastern Utah. There's no effect on the vegetation. There is no vegetation out there. It's a pretty barren desert. The nice thing about that is it's beautifully exposed for the geologists in the room, at least for me. And you can map out the travertine deposits and how they relate to the fault structure. So the fault is not just a linear planar element. It has complexity to it. It bifurcates and converges. And the travertine deposits are preferentially in places where the fault is branch points. So this shows a 3D block diagram of this fault and the layers. That's the Green River here. The crystal geyser would be here. The paleo fossil seep sites along this fault trace. We know that there's a significant aquifer underneath, the Navajo aquifer. There's also brine migrating up from greater depth from Paleozoic layers, and then they mix, and the CO2 comes mostly from crustal sources and the Paleozoic, and then it gets to the surface. So we have a pretty good understanding how the system works. A fair amount of research has been done over the last 10 to 15 years at this location, the various groups, because it's one of the few sites where we can actually see a CO2 leak or seepage in a sedimentary system in action. And it's well exposed. And something that those exposures contain is the topmost layer here, which is called Mancos Shale, could be seen as a caprock. You know, in this case, obviously the erosion has removed it in part, so it's not complete seal anymore, but it could be seen as an analog for caprock in a CO2 sequestration reservoir. And something that is readily apparent if you go out there is you see fractures with those alteration halos. And that alteration is because of the CO2 alteration interaction with the shale. There's two images here of the shale about 10 meters from the fault, and then at a larger distance away from the fault. And there are fractures also in the shale away from the fault. And this may be in part because of surface exposure, but the fractures are very different. They are much more connected in the vicinity of the fault, and they have those alteration halos. So that's the CO2. We think this is the effect of the CO2 weakening the rock and altering the rock, which we don't see if we go away from the fault. Now, in addition to the difference in the fracture style, we see that the shale gets altered in the vicinity of the fault. And those diagrams are the mineral composition of the shales as obtained by X-ray diffraction analysis. And different colors are different mineral components. The quartz is in blue, the illite, which is a clay, is in red, and then the light green is calcite, which is a carbonate, and then some other carbonates. That is, to the left, is the unaltered, so to speak, unaltered Mankell shale. But in the vicinity of the fault, we see that the composition is quite different. Calcite is the dominant mineral phase. So as the CO2 migrates, or the brine that is saturated with CO2 migrates through this shale along the fractures, it precipitates abundant calcite in the pores, and it's also replacing some of the minerals. So it's both, it's precipitation in some pore space and replacement of other mineral phases. So yes, the chemistry is real in this case. So then the question is, what does this do to, how does it affect the leakage processes? So the problem statement here is, so as I said before, we want to make sure that the CO2 reservoirs have efficient seals. The number that is reported here, people want to be more than 99% efficient. And the time scale here is basically the time scale of human civilization. So it's not just 100 years, it's the 1,000-year time scale. We have extensive experience analyzing top and fault seal risk in oil and gas systems. But this is somewhat different. In oil and gas systems, it's mostly a mechanical issue. We don't want to exceed the frac gradient, and we don't want to reactivate faults by exceeding the Coulomb failure stress. But in this case, since the CO2 is interacting with the brine, and the CO2 charged brine is interacting with the rock, it is not just a physical process, it's a physical and chemical process. So this is a little bit different. It's a little more complicated. So this project that I'm reporting on here was concerned about what would those chemical effects be. And we did this at the very foundational basic research level, just to see how shales are affected by chemical interaction with brine in terms of fracture processes. So the focus here is on fracturing, not so much on fault reactivation, but faults are composed of fractures. So if we understand fracture mechanics in faults, then we have some understanding of the fault mechanics as well, especially as it addresses the leakage behavior, the flow behavior of the fault. So the key word here is chemically assisted fracture growth, which is obviously not a new topic. It's in engineering materials, it's well known. There's basically two types. It's called stress corrosion fracture or subcritical fracture growth. And what that means is you have probably personal experience with this. If a rock hits your windshield on your car, two things could happen. Either it just shatters and explodes. That would be critical fracture growth and failure in seconds. Or it hits your windshield and then you see fractures growing across it, and it could take perhaps days or weeks before the windshield just falls apart. And sometimes it's on a rainy day that you see the fractures going across your windshield more quickly than on a sunny day. That's because the water actually aids in this stress corrosion fracture. So that is called subcritical fracture if it is slow and not rapid, like a runaway rapid fracture propagation that would be considered critical. So rocks show the same behavior. We can test them and they fail critically, or we can test them and they fail by slow subcritical fracture. And in this case, we are concerned about fracture growth, not so much in the reservoir that would perhaps enhance the permeability of the reservoir, but primarily from the reservoir into the overlying caprock and into the shale. So what we have done is a series of laboratory fracture mechanics testing in chemically reactive environments. So we submerge the sample in a bath of water with varying pH and varying salinity and so on, and then conduct some fracture mechanics tests, which are done on little plates that are 1 inch wide, 2 inches long, and a few millimeters thick. And it's the setup is actually providing a torque on the sample. So it's not ripping it apart, it's tearing it almost. like a sheet of paper, and the fracture is propagating along the middle of that plate. Okay, and that stress is applied to this plate while the plate is immersed. So in this case, you can go as high as 65 degrees centigrade. We cannot do this using this setup under reservoir conditions. So this is ambient stress. And what we see is in a schematic on the left, that's a plot of a log of the stress applied versus the log of the velocity of the fracture as it propagates. And if you exceed a critical stress, then the material fails critically. That's at this dashed line. That's the critical loading stress, or the fracture toughness. Below that, the fracture would propagate in this log-log space at a shown as a linear velocity dependence here. And then as it as you increase the stress, and as you increase the stress approaching the critical stress, then it would just go off and fail critically. So what we're measuring in the lab is the fracture toughness to rapid loading, and we measure the slope of this line here, which is known as the subcritical crack index, or SCI. Okay, so this SCI is the exponent in this velocity equation. So there are two tests here. One is for the critical failure, where we load the sample rapidly. So this is time in seconds versus the load in Newton. And then the little plate fails instantaneously. So we measure that stress, and then we do separate tests where the loading rate is somewhat slower. And there are repeated cycles of load and relaxation. So we load the sample, let the fracture propagate a little bit, let the sample relax, and then load it again, relax, load again, relax. So we get multiple tests out of the same sample actually, and the decay of this load of this relaxation line gives us the subcritical index. Okay, so those are the two parameters we measure, and because we are looking at the foundation of those processes, not so much necessarily just what would be applicable to CO2 sequestration, we use 3 different shales of different rock composition, because rock composition matters, and shales different composition. We did it at room dry conditions, in dry CO2 gas, distilled water, and then the varying salinity of the water with sodium chloride, potassium chloride, different pH, and room temperature 65 degrees centigrade. This is as high as we can go. And then we also did some things where we coat the sample to limit the reaction to the fracture tip. I'll show this in a minute here. So 3 rock types to kind of cover the range in shale compositions. The Woodford shale is very quartz rich. Those are scanning electron microscope images that map the chemical composition. So all the red is the quartz. So it's dominantly quartz. The Marcellus shale, on the other hand, is very carbonate rich. It's almost a limestone in this case. So it's all this blue here is calcite. And then the Mancos shale is somewhere in between. It's less quartz rich than the Woodford, but not as carbonate rich as the Marcellus. Okay. Some images of what the fractures look like under the microscope, actually the SEM. They are usually going around grains, except in the Marcellus, which has all this calcite in it, it goes along cleavage planes. So that's one example here of the testing results. So this is again the same plot that I showed in the schematic before. That's stress intensity factor versus velocity. So those are those linear segments in that response curve I showed before. And you see that they plot differently if it is dry CO2 gas versus ambient air versus water. So having dry versus water saturated samples makes a big difference in general. And that affects the fracture toughness, with water weakening the rock, but also the subcritical index. So water weakens the rock, and if you look at rock mechanics data in the literature that are done on dry rock at room conditions, they would not replicate conditions that are expected for water saturated subsurface conditions. Okay. Now I mentioned that we coat, so if we just submerge the sample in the water, then the entire sample gets weakened by the water. But what we want to do to replicate the conditions of a growing fracture in subsurface, the chemical reaction may be limited to the fracture tip or the fracture inside. So we coat the entire sample with a hydrophobic material, but just leave the fracture uncoated. So then the only reaction is limited to the vicinity of the fracture. And that shows some interesting nonlinear behavior because the rock does not react to the water until the fracture creates access to it and the water permeates the rock in the vicinity of the fracture. So it's a very interesting response that is shown here on the right side without going into the details here. So the next examples are varying salinity. As we know from reservoir engineers know that salinity affects clay swelling in the subsurface. So we also see that effect in our samples. And it makes a difference if you use sodium chloride or potassium chloride. Most relevant to CO2 is changes in pH. In principle, if you inject CO2 into water, the pH could go as low as 2. But it depends. It could be much less depending on the buffering capacity of the rock water system. So in this case, we use HCl for convenience and go as low as 0.8. It has little effect on the fracture toughness, surprisingly. But in a carbonate-rich rock as the Marcellus Shale, it has obviously a big effect on the subcritical index. And if you think about bringing this back to daily experience, if you're not a chemist, if you're trying to remove the scaling on your kitchen faucet, that is calcium carbonate, if you just apply that cleaner and wash it away, it will not do much. You will have to let it soak in for minutes, maybe an hour, right? It's time dependent. So the dissolution of the carbonate is not instantaneous. It takes time. And that manifests itself measurably in the subcritical index. The slow fracture growth is affected by this. The rapid fracture growth is not. Okay. Now, wrapping this up, how is this relevant for failure of a caprock? We have used a boundary element code that Dr. John Olson has developed over the years. It's called joints, and it's one of the maybe the only code that I know of that allows to model easily the subcritical fracture effects. So we can input the subcritical index and then apply a loading rate to the material and then watch how the fractures are growing over time. Okay, so we have done this using the parameters of our laboratory results for the different rock types and for the different fluid composition. And you should envision this as a cross-section view of the caprock, the little seed cracks that we need for this boundary element code. And then we watch how those fractures nucleate from the base and migrate upward from the bottom up. And this is shown here now for 1,000 years, and the time scale is not really absolute here. So we're looking at relative differences. And you see, for instance, that the dry CO2 has the least amount of fractures. The sodium chloride systems have a lot of fractures, and the HCl, the acidic brine tests have something intermediate, right? And the Woodford, which is the carbonate one, no, the Marcellus, the carbonate one, maybe a little more than the other ones. But what that also means, if you plot, we can then do some eclipse type of flow simulations across those fractures, across the layer, and then we can look at the permeability evolution over time. And again, we shouldn't take those absolute years at face value. It's all relative here. But ultimately, we get connectivity across those layers, and then the fluid will leak across. If it's the dry CO2, as shown here in the heavy line, it's the last one to form fractures. But once the fractures go, then they create a lot of permeability across, right? The more reactive systems, they start earlier to grow fractures, but then they get overtaken by the critical fractures. This would suggest that the chemical component could initiate fracture growth earlier. But depending then on the thickness of the shale, it may stall. So in terms of practical application here, the reactivity of the system can matter, but the shale thickness as well. You want to avoid systems where the rock would react significantly with the brine and the CO2 saturated brine. And you may want to check that the reservoir, and particularly the caprock composition, is such that it minimizes those chemical effects. So the takeaway points here, yes, fault and fractures can be conduits for CO2 leakage. It happens in natural systems. Unlike oil and gas applications, top seal risk assessment, in this case, we need to be concerned about chemical effects. Chemical effects of the dissolved CO2 in the brine, and then that brine interacting with the caprock. What the extent of those chemical reactions depends on the rock mineral composition, so it's specific. I should also mention it could also be specific to the reservoir mineral composition. The buffering capacity in the reservoir would depend on, for instance, the amount of calcite in it. And then, depending on the chemical conditions, we may have to expect some time-dependent subcritical fracture propagation that may not manifest itself initially. It could take perhaps 100 years. And since those are slowly occurring fractures, the thickness of the caprock would matter here. All right, I think with that, I would be happy to answer questions if you have time. No. Thank you.
Thank you very much, Dr. Eichhubl. Joseph, do you have questions? No?
Yes. Thank you so much for your presentation. We have one that says, what can simulation do by considering geomechanics to avoid CO2 leakage through induced natural fractures or reactivated faults at the condition of higher CO2 injection rate to make more CO2 be fixed? And do we have a balance?
So I'm not sure if I get all parts of this question, but so I should emphasize, we looked here at fracture growth, right? Or what we call mode 1, opening mode fracture growth. The whole topic of leakage is also reactivating a fault, which is a column failure analysis, which we have not done here, but that will depend on the rate of pressure increase in the reservoir. So the primary control measure here would be to monitor the pressure in the reservoir and keep it below the column failure stress of a fault, provided the fault is known, location is known, and provided you know the orientation of the fault, because the failure stress would be a function of fault orientation relative to the stress field. But this is not something that I focused on here. There may be chemical effects on fault slip as well, but I believe the primary effect there is mechanical. What I focused on is the fracture growth that would go along with fault reactivation, and ultimately it is the opening mode fractures that provide the fault conductivity for flow. So the slippage of the fault itself may create an earthquake, but it is actually the opening mode fractures that would then provide the conduits for this CO2 to migrate along the fault. I'm not sure if I answered the question, but since faults reactivation was brought in, it is a function of the reservoir pressure, and that needs to be monitored.
Yes, thank you so much. We have another one. It's a little bit large, but says, rather than using a seal cap to store CO2, can we inject CO2 very deep in the reservoir for when the CO2 migrated upward, most of the CO2 is maintained within the reservoir and close to none goes back to the surface?
Yes, so Dr. Delshad showed this example of stacked aquifers, right? So you have a reservoir at depth, and then you have 3-4 layers on top, alternating shale, sandstone, shale, sandstone. That's what we would expect. Typically, we would not have just a single sealing unit. We would be in a system that has multiple porous layers on top. Now, that would be the preferred option because it provides you some redundancy. And as we have seen in the simulations, the CO2 may migrate across the first seal and maybe the second seal, but then the third seal may hold, right? And before it gets to the surface and before the CO2 migrates into the groundwater aquifer that provides perhaps drinking water, right? So yes, that would be the recommended practice. But the other aspect I mentioned is also the thickness of the shale layers. So if it's many thin shale layers versus one thick one, I'm not quite sure what would be the preference here. That would have to be looked into detail, you know. So it takes both. It takes thick layers, but also multiple layers for caprock, for an effective caprock.
Thank you, Dr. Eichhubl.
Maybe one more questions because we are running late.
Yes, this will be the last one for Dr. Eichhubl. Do we have any study for the chemical reactivity of supercritical CO2 with carbonates and silicate formations over time?
So we were partnering with Sandia National Labs, and they did similar fraction mechanics tests in a confined system with supercritical CO2. And I cannot report those data because it hasn't been published yet. Qualitatively, what I showed without the subcritical CO2 holds as well. It's the amount of water in the CO2 that matters here. If it's very dry subcritical CO2, it's rather inert. But if you have water dissolved in that subcritical CO2, then it becomes reactive. So yes, there has been some work done. And there has also been some work done on just reacting rock with subcritical CO2 without the fraction mechanics system.
Thank you very much, Dr. Eichhubl.
Yes.
Very interesting talk. Thank you.